we're off, right. Okay, so so what you've missed, Lily, you've just gone through 6 and 7 and done part B, but I'm sure you can catch up with that. So now, wouldn't it be good? You know me, I like when different parts of maths mix together. I mean, you know, I love nothing more than a bit of binomial expanding, but I also love a bit of partial fractions. So, you know, you can guess what my favourite sort of maths problem is. That's a problem that combines both partial fractions and a little bit of binomial expanding. And, you know, as I've said, the maths syllabus is so vast, and at the end of the day, you're just going to get, you know, well, it's 2 pure papers, so you might get 40 questions. So they've got to work out how to cover as much as they can. So this sort of question is the sort of question they love. How do I know this is a binomial expansion question? Well, we'd say here, show the cubic approximation. So that's not a phrase we've come across before, have we? But don't forget, the binomial expansion isn't really an expansion, is it? It's an estimation, an approximation. So that was the clue there. Why do I know that I'm okay to partial fraction this straight away without doing any division first? James, what is it about that expression which means I'm confident to go for the partial fractions?
Yeah, the denominator's got an extra power there.
Yeah, so the order of the numerator is 1, and the order of the denominator is 2. And for partial fractions to work, you need to have an order on top that's 1 less than the order on the bottom. So here we go. This is a good test of how we've been getting on with our mock revision. How confident are you to partial fraction that up? So can we all agree that we're going to write it as a over 1 plus x and b over 2 minus x? And see if you can partial fraction that up.
What should I title this?
Right, so this is partial fractions and binomial series expansion. If you're not clear on how I've managed to go from there to there, I've skipped several steps, haven't I? Please make sure that you review that. So we've got videos on partial fractions, if you don't want to come and talk to me, or I'm very happy to talk to you, or it'll be in the revision guide, or, you know, this is absolutely sort of route 1, bread and butter stuff, so please make sure you're okay with it. So I'm hoping that we're okay with that. And you've got a choice of writing plus -2 or just writing -2. It means exactly the same thing, and the two are just as good as each other. So we're then asked to write a cubic approximation for this, which is where the binomial comes in. Now, just like before, where we had a binomial and then we multiplied it with something else, this is a similar thing, but we've got two binomials here. Am I? Yeah. So we've got two separate parts to this answer, this partial fractions answer, both of which can be written as binomial style expansions. So the first term I could write like this. The 3 isn't to the power of -1, is it? The 3 is just sat separately. So I can expand that, and remember, powers of -1 are quite nice. You get quite nice patterns in the answers. And I just then multiply my answer by 3. So I'm going to do my binomial thing and just triple everything. The second one, not quite so nice. It's got a -2 outside. I'm including the minus in there, and then I'm just going to add my two answers together. So I'm effectively dealing with it as plus -2 like that. I think that's going to be easier. So that's 2 minus x to the power of -1. But of course that is one of those ones where you haven't got a 1. So I've got to pull something out of that bracket. So I've got to be careful here because I've already got a -2 out the front before I do any of that. So maybe time for a colour change. So I need to pull a 2 out, but it's not 2, it's 2 to the power of -1. And then divide the things in the bracket by 2. So that's an example of what we were doing yesterday and what we've just practiced at the beginning of today. So I'm going to redo that in blue so it's obvious that. So this term can be written like that. And this term can be written like that. And then this term, nice and easy. But this term I've then got to do the pulling out bit. But there's good news, isn't there, out the front here? Because that's 1/2, a half, 2 to the power of -1. So -2 times a half is -1. So actually, that's going to be okay. I've got a -2 out the front already. I've just pulled out a 2 to the power of -1. So actually that's just going to be -1 times that expansion there. I'm going to give myself a bit more space for that one. And then at the end, when I've multiplied them all out, I'm going to add my two answers together. And we should, fingers crossed, get that. Have a go. So you're doing the binomial series expansion of 1 plus x to the -1, which is about as easy as it gets really, 4 terms. And you're doing the binomial expansion of 1 minus x over 2 to the power of -1, and multiplying that by -1. Have a go. the second one, make sure that you do x as minus x over 2.
How many expansions are there?
4 terms. So up to the x cubed term. Yeah, 1 always counts as a term. Sorry, I just realised I've written partials fractions.
Just so you know, we're down to our last. I've just tried photocopying it and making it darker, which is the quality is awful. Yeah.
So when n is minus 1, these always cancel out. The only thing you've got to be careful about is the sign. So I end up with 3 lots of that. So that's 3 minus 3x plus 3x squared minus 3x cubed. And don't forget, this is part of an expansion, so that's just as far as we've gone. And then this one, it's just minus 1 times all of that. So that's minus 1 minus x over 2 minus x squared over 4 minus x cubed over 8. So I'm fingers crossed here when we add those two answers together. So I've got 3 and minus 1, which make 2. Bingo. I've got minus 3x minus half an x, which is minus 3.5x, 7 over 2. Tick. I've got 3x squared, take away a, oh, sorry, I don't know where that 4 came from. take away 1/4 of an x squared, which gives me 2 3/4, which is 11/4. Tick. And I've got minus 3x cubed, take away another 1/8 of an x cubed. So that's 3 and 1, minus 3 and 1/8, which is 25/8, minus 25/8 x cubed. A quick word about validity. I've done 2 expansions in answering this question. I expanded 1 plus x to the minus 1. Remember, we said this yesterday. Anything that you start with is irrelevant in terms of validity. It all depends on the thing you expanded. So I expanded that, and for that, x had to be between minus 1 and 1. I also expanded, by the time I'd simplified it, 1 minus x over 2. So that had to be between minus 1 and 1, which means that if I multiply it by minus 1, change the signs and then flip it around, you get that. So I've got 2 validity statements and I have to use the strictest. So the strictest is that one. So this whole answer is only valid when x is between minus 1 and 1. It's the stricter of the 2 validity parts. So although this is valid when x is between minus 2 and 2, because the other one is only valid between minus 1 and 1, that's what I give as my answer. Yes, Pat?
How do the equalities work again? So is it when you change the sign, is the...
Yeah, so for that one there, if I multiply, what I would do is multiply by minus 2.
Right.
If I multiply by minus 2, that becomes 2, and that becomes minus 2, and the signs flip.
Oh, okay. Yeah.
But then I've just written it that way around again, so it's... So we use the stricter of the 2 validity statements. Even though the second one is valid when x is between minus 2 and 2, because the first one was only valid between minus 1 and 1, that's the one we have to use. Now you'll be pleased to hear that I'm not going to get you to do another one of those in class, because they're quite horrific, aren't they? They're quite long. But I do think it's worth doing one independently. So have a go independently at question 4 on page 103, and we'll have a little look at that one next lesson. And I mean, the good news is they're both 1 plus somethings. So that's page 103, question 4. Again, it's an OK to partial fraction 1, because you've got a numerator of order 1 and a denominator of order 2. Now I've videoed that, so these are pretty horrific, so feel free to look back at the video. I won't email you all the link, but it's hopefully you're all subscribed anyway, so it's all, obviously. Smash that thumbs up, and no, I'm not monetizing. I'm about 100,000 subscribers short of being able to monetize. So one day, maybe. Right. I think we need a bit of light relief. Yesterday was National Poetry Day. Did I mention it is National Poetry Day? So I thought, let's have a poem. There once was a lady called Bright, who could travel faster than light. She set off one day in a relative way and arrived back the previous night. Oh, tough crowd. Goodness me, I thought it was quite good. There you go. Oh, well, Joe will be delighted, because it was like the same thing with the other thing. I said, I bet the other group will laugh. So there you go. They didn't.
I thought it was going to keep going. It was really funny.
I always leave the audience wanting more. Okay. we're moving on. This next topic is the last thing that I'm going to include on the mock exam. We're going to get a bit further than this particular topic before half term because we've got 2 weeks. But this next topic will be the last one. And you'll already be aware, if you've got the revision schedule next to your toilet and your mirror, that it's radians. You may not know what radians are, you may have an inkling, you may have come across them before in another subject, but there we go. Before I talk about what a radian is, can I give you a little question? Here's a sector, that angle is 50 degrees, and the radius of the sector, so it's part of the circle, is 4 centimetres. Can I get you to tell me the arc length? That's the curvy bit, which is part of the circumference of the whole circle, if it was a whole circle. And can I get you to work out the sector area? So that's the area of that thing, which of course is part of the area of the whole circle. So in both cases you need to be thinking about what would it be if it was a big normal circle. So you've got to remember your formula for circumference and area, and then we've got a fraction here. And actually, I'm not worried about the actual answer. I'm more interested in the sum that you're going to write out. So don't worry about the actual answer. Let's just write out the sum, or you could leave it in terms of pi, maybe.
That sounds about right.
So go on, Jodie, talk me through how you'd work out the arc length. Not necessarily bothered about the answer, I'd just like to know how you sort of your calculation.
50 over 360 times pi times diameter.
Yeah. In fact, we could sort of change that into a general purpose sort of formula, couldn't we? Theta over 360 times pi. So in this case, it's 50 over 360 times pi times 8. We happy with that? Because the diameter is 8. And Beth, what about sector area?
We did 50 over 360 times pi times 4 squared.
Brilliant. Yeah. And we could sort of write that as a general formula, couldn't we? Theta, remember we would often use that Greek letter theta, times pi times the radius, correct? And you know, we've done that at GCSE, and like a lot of things we've done involving angles, you know, we can do it using degrees. The other big thing we do using angles is trigonometry, where we've been solving equations or finding missing lengths in triangles and other shapes using sine, cos and tan. We've done all that in degrees. What radians gives us is an alternative way of measuring angles. Now, at first, radians seems unnecessarily complicated, but there are some things which it makes really, really easy.
Yeah.
Let me explain to you what a radian is. Here is a circle. Here's one I prepared earlier. Here is a radius. If I took that radius and bent it and stretched it around the outside of the circle, it would probably reach something like that. The angle that that creates, we say the angle that subtends, is called 1 radian, often abbreviated to rad. When I was young, that meant cool when I was young. 1 rad, yeah. So a radian is the angle you get by stretching a radius around the outside of a circle. So how many radiuses fit around the outside of a circle? 2 pi. Yeah, it's 2 pi. It's about 6, isn't it? It's about 6. The circumference of a circle is pi times the diameter, but a diameter is 2 radiuses. So the circumference is pi times 2 radiuses. And have you ever wondered why people reorder it and say 2 pi r? Well, it's because of this. Yeah. So how many degrees in 1 radian? Well, that's a really awkward number. But how many radians in 360 degrees? Well, that's nice. Oh, what happened there? That's quite nice. So rather than telling you that 1 radian is roughly 57 degrees, which it is, I'm going to ask you to remember that 360 degrees, a full circle, is 2 pi radians. Abbreviation of. And that's all I remember. That's all I remember. So, okay, I could work out 1 radian. It's 360 divided by 2 pi, which is roughly 6, isn't it? So it's just a little bit smaller than 60. You get 57 odd. But we don't actually, well, I suppose it's useful to know that, but I rarely bother with that. I'm much more interested in this fact here. And as I said, at the moment, you might think, why on earth bother with a different way of measuring angles? We've used degrees since we were, at primary school, and we know that 90 degrees is a right angle. Well, look what happens to my arc length and sector area formula if I switch into radians. Okay, so if instead of saying that that was 50 degrees, my angle was in radians, so it was still use theta, but it's theta radians, and let's call that r. Okay, so I'm going to talk about this, and are you happy if I rewrite this as 2 r's? Diameter is 2 r's. So let's look at what happens to this formula when I switch to using radians. So the fraction of the circle is that many radians out of a total of 2 pi radians. And that means something rather special happens. Let me write it as one big long sum. I've got theta times pi times 2r over 2 pi. Well, I'm left with theta times r. When you are working in radians, the arc length of a sector is just the angle multiplied by the radius. If that angle is measured in radians, a whole lot easier. A whole lot easier. If we can force ourselves to use this different measure, it's a whole lot easier to work out things like arc length. It's just the angle multiplied by the radius. Now, okay, it's not very complicated if it's in degrees, particularly for capable mathematicians like yourself. But this is one example, and there are numerous examples of how radians make that a little bit easier. Do you want to see if you can simplify the sector area formula in the same way? What happens to the sector area formula if we switch to radians instead of degrees? not such fun this time, but we can still cancel out the pi's. So we're left with theta r squared over 2, which is often written as a half r squared theta. And in fact, this is often written as r theta. So theta r theta, doesn't really matter which way around. But it's one place where if we can force ourselves to use radians, that bit gets a little bit easier. So next, that's one of the things we'll do is we'll do some arc length and sector areas. The other thing that gets easier is dealing with our trig graphs, although it's one of those things that it hurts a bit to start with, but after a while, everything gets easier. So let's have a little think about this. I've said how we don't often worry about that conversion, but we do use values which we are familiar with in terms of the trig graph. So I know the trig graphs repeat, for example, sine has a period of 360 degrees, and it's sort of broken into quarters, isn't it? So can you tell me how I could write those numbers in radians? And what about some of the other sort of key values that we get? So for example, what about 540 degrees? How could we write that in radians? Or what about 120 degrees? What about that? And 60 degrees? And maybe 45 degrees. Can you see if you can write those in radians? It will involve pi. Every answer will involve pi. So 360 is 2 pi radians. So Charlie, 180 degrees, how could we write that in radians? Pi radians, yeah, just pi radians, yeah, brilliant. And Tegan, what about 90 degrees then? Half of pi, yeah, which we tend to just write as pi over 2. Yeah, pi over 2. Radians, that's good, yeah. Okay. Isabel, what about 540? Which is 3 lots of 180. I can't remember noting.
3 pi.
3 pi radians, yeah, that's right, yeah, yeah. And go on then, George, 120?
Oh goodness. No, 2/3. I was right first.
2/3, yeah.
Pi radians.
Yeah, that's right. So we tend to write that as 2 pi over 3. But yeah, 2/3 pi, 2 pi over 3, same thing, same thing. James P, what about 60 degrees? Can't be noticing I've got 180. Pi over 3, brilliant, yeah, pi over 3 radians. And 45 degrees, well, it's going to be pi over 4, isn't it? Pi over 4, because 90 is... Yeah. More of this next week. So you've got that one question to have a go at, and yeah, all good, all good.